we are just going to solve system of equations. Okay, this is a solving system. This solving system of equations. That's linear equations, simple. So the very first thing is a homogeneous thing. 1, 2, 1. Right. So we don't need to write the variables. So 1, 2, 1. 4, 1, minus 4. The people may have already done it, but then you can help me do it faster. We will just apply the row operations and okay, and not worry about the other things because we have already proved those. That the solution is preserved. Solution doesn't change. System changes, but solution doesn't change. And yeah, and other things. So because b is equal to 0, so our this thing is, but I will just erase it now. This is equal to this. Okay. But because we are only dealing with 0, 0, so we will not write it. So let's see what the system becomes. Yes. And then what happens? What are these? This 2 will become 0, 0. But how will this change? Will have done it.
That is -6 -3 1
Nice. Last one.
and also -6 -3 1.
Okay. Yes. This is good for us. So you
Sir,
can
actually your voice is break. Sir, can you hear me?
yes, I can hear you. Is it same? Is it still breaking?
Yes, sir. Yes, it's still kind of
Still.
breaking for
Okay,
me. I
okay,
don't know if
okay.
it's
Yeah, so I will maybe I should change the connection. Yeah, let me see. Actually, I'm in a different room. Is it still breaking? Yes.
I think now it's better, sir, actually.
But is it fine? I'm clear?
Yes, sir, now it's better.
Okay. Right. Otherwise, I can still do something. All right. Let me know. Anyways.
No, now it's
fine. Okay. Right. So and what do you do after this?
Then again I did 3 R1 plus R2, that is 3004.
Right. 3.
0.
Okay. 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 So you are okay. I get it. Yeah. Right. Right. So you're doing 3 times this and then you're adding this. Right. So yeah. So I will do it slightly. Yeah. 1 by 3 of this. So this will become 0. And this will also become 0. And this one will be 2 by 3.
That would be 4 by 3 is, I guess, 4 by 3.
Oh, right. Correct. Yeah. Right. And then this is -6. So that also we should change. Divide by 1 minus 1 by 6. Fine. Okay. So let me just add some things here. Okay. By the way, I just forgot to tell you, sorry to interrupt in between. But what I said about equivalence of matrices, basically I've said everything that is needed kind of elementary level. But still, if you have the time and patience, there is a book by, okay, I don't know if it is Satish Shirali or Shailesh Shirali, I don't remember, but just Shirali and Vasudev, I think Hari Vasudev or someone. I don't remember very well. But metric space. The name of the book is Metric Spaces, and there is a chapter or portion there. It's very well written. Obviously, you will find it in any book. Rudin will say it in 2 lines or something, but but yeah, in this book it's very well done. So I'm just telling you the reference. There are hundreds of books and analysis, but I like this one for that topic. Okay, so that you can check out. But yeah, so coming to this, let us now just write the solutions. Then I will tell you what more we have learned here than what is there in R10, at least in the text. So how do you write the solutions? The idea behind doing this is clear without words, but you see, so is it the columns? So we are applying the operations on rows, but think about it. It is the columns that are sort of distinguished from one another in features, right? So it indicates that you should make definitions based on how the columns are. So if you see the columns in which there are ones, right? So those columns which are like the first member in their rows, which have a non-zero entry or one as an entry, in those columns, the whole rest of the column is zero, right? So you see what I said, right? And these columns are called pivot columns. I can write a definition, but I am not doing it. But these are pivot columns. The idea is that you want to solve for the rest of the, because the variables correspond to the columns, right? Second column is second variable, third column is third variable, and so on. Okay, so right. So the idea about doing this is like solving for these two variables, x1 and x2, in terms of the other variables. So you can think of it like that, like the value of x1 and x2 will be completely determined by the other values. So those are the things ways you can think of. Okay. So let me just then write it quickly. So x1 would be equal to, fine. I'm not writing too many definitions now, but maybe just write as x4. And x2 x3 1 by 6 x4, and obviously x3 x4 are free. So those are the free variables or free columns. So your entire solution set is this. Anything that is not written here should not be assumed, right? Which means that x3 and x4, nothing should be assumed, they are free. Fine. Okay.
Yes.
Right. So this is very straightforward. So you see, so what more can I say, right? Without introducing more terminology. Yeah, we should start talking about some dimensions and so on, right? What is a dimension? Obviously, roughly you understand the dimension is 2. Okay. But first of all, where does the solutions live in? Where is the solution live in? Where is this? This is in R4, right? So we start trying to start using the language of geometry. This lives in R4. and you want to say the dimension is 2. Anyone would say dimension is 2, right? 2 free variables, 2 free terms floating around. So can you give me 2 vectors which generate all the solutions from looking at this, right? Yeah. So you can, right? So you can write maybe something like this. X1 I'm jumping, but you try to absorb it, okay? You take this vector and you take this vector, right? Using these 2 vectors, you can get all the solutions. Is this correct? Right? Because this is the same set. Okay. So you can see this is the same set. Yes or no?
Yes, sir.
Right? Yeah. You can see just add it for coordinate wise, and you can see. Just add the first coordinate will become this, second coordinate will become this, third and fourth. And I've not done any magic, right? I have just taken x3 times this column, which is what this equation is saying, right? Nothing more than that. And x4 times this column. That's all I've written, nothing. In fact, that is more easier than solving. Okay. So we
I'm
have,
not getting it.
right. Yeah, that's fine. So, yeah. So how should I say then? Yes. Either we can first let us say it from here. Okay. Yes, because I was jumping. I know that. So not a, so yes, you can write this. Right. So let me see. So let's erase this. So first you agree that the solutions live in R4. So let us try to write this. These are points in R4, right? There are 4 tuples points. Solutions, every solution is a 4 tuple, right? X1 ka value, X2, X3, X4. These 4 values will give you a solution. Find all those values. To find all, we're basically interested in a subset of R4. So you see, if you write it first directly like that, then it is this. This is just, I've copied the same thing. In fact, this is the correct way to write. That is not a correct way to write, actually. This is not in R4. I mean, in some sense, right? Yeah. Okay. Arnav, is it okay?
Yes, sir.
This is fine, right? I've just written the solution, x3, x4, and yeah. This is fine. Now I'm just saying that you can, yeah, just break it. Just write it as sum of 2 vectors. So if you just break it in the natural way, then what is it? So breaking natural way means that keep the independent, you see. So this thing plus this thing. X4 and X3 are free, so this is not one vector. It's a, yeah.
Sir, I get it.
It's trivial, right? Yeah. So a trivial
Sir,
thing,
sir.
and you can even see it from here. Yeah. But obviously, these are some new ways to write things. Once you see it, it's like, okay, it actually makes life easier. So that's why we are doing it, right? Okay, so we have learned some interesting things. You know, these will, you can use this to later on prove many other interesting things. these are called row reduced echelon forms. May have done it at some point. These are unique. But yeah, I can actually give some homework and then end. Okay. So, but yeah, before that, let's look at the rest of the problem, rest of this problem. Okay. So we have learned these things, and if you want to read these things in detail, then you can consult Hoffman and Kuhns. Yeah, but obviously, how many books to read? So that's an optional, of course. Yeah, Hoffman and Kuhns, chapter 1. I think he calls it chapter 1. Some books maybe call it chapter 0. Okay, so yeah, so a lot of books the first chapter they say is chapter 0, not even a chapter. But I'm not. But Hoffman and Kuhns is not. Which books? So there are some books like that, right? I remember. Yeah, I think Moncrief. The whole first section is section 0. Oh yeah, Hatcher. Yeah, Hatcher. If you look, the dreaded book in algebraic topology. Yeah, he calls the entire first chapter chapter 0. Nobody actually completes. And then that's the reason why the rest of the book becomes strange actually, because it becomes very difficult to. Not that I have solved it. I'm yet to learn it properly. I've just done first 2 chapters. So, anyways, what was I saying? Yeah, just the rest of the thing. So you see, okay, so I should not erase it. You see, the job is very simple, but we can also learn some things here also, which you will be applying when you do differential equations. It's very important. But before saying that, so you have this system, right? So basically, obviously, you have to apply the same these things to this vector 1, 1, 0, right? I don't know if you have applied. You have to apply and see what happens. Okay? You have to apply and see what happens. So have you anyone worked out what does this vector become? No?
I have done. I've
Yeah,
done that.
you can. If you have it with you, it will be very good, because I cannot. I think I cannot calculate.
It's not giving any solutions actually.
Right, but what does this vector become?
Oh, it's coming 1 minus 2 1.
Right, 1 minus 2 1, and then as you were saying, it doesn't give any solutions for this reason, right? And you can see that this kind of phenomena that is happening, this kind of phenomena that is happening, this is the only reason why, this is the only way in which you can end up having no solutions, right? Meaning that a 0 row, but the corresponding constraint is non-zero, right? The right hand side in that row is non-zero. That is the only situation in which you can have no solutions. Correct? You're not doing part 3, it's a repetition. Okay. So in this case, there are no solutions, and you can wonder that when it was 0, 0, 0, then there were infinitely many solutions. But when it is some constant, then for this constant, there are no solutions. Right? Constant meaning that for this vector, right? For this vector, there are no solutions. For 0, 0 vector, there are infinitely many solutions. And what is happening? For which vectors will there be solutions? Can you describe all those vectors? Yeah. So those are some interesting questions, right? Just give me a minute. Yeah, that. So if we had one plane, if we had only one, yeah. So you can also notice this thing, right? which is like the starting point to try to understand this. There was only one, so this is just some extras. I'm just saying, okay, try to follow it. We can build on it later, but just think, right? You see this kind of situation that we are in, right? Where you have a row which is 0, and then you have a non-zero, so there are no solutions. If you take a simpler case of this, which is only one equation. If you only had one equation with some 4 variables, fine, but only one equation. In that case, this kind of situation can never happen. Agree with me or not? Right? Yeah.
Yes, sir.
Yeah. In that case, right? In that case, the zero set, for example, can take a trivial example. If you take something like this, so you know that this is a hyperplane. This is a plane in 3 dimensions that passes through the origin. Right? 0, 0, 0 is there in this, satisfies this, and so there's a plane. Right? You can see that. If you don't see that, then you can think about it. And then if I replace the 0 by a constant, then what is that doing? Well, that is just taking the plane and translating it. Right? Yeah, it is just taking the plane and translating it. So that is yeah, because this will also be a plane, but it doesn't pass through the origin. It is a translation, right? And therefore there are points on it, and those points is what we are wanting, right? That's why it doesn't happen in one dimension. Obviously it doesn't happen because you know it doesn't happen. You can, that's why you said it's yes, but that's a geometric reason, right? So there is a plane, so let's we can talk about this next day. So this thing is a plane, right? XYZ coordinates. I'm just drawing a portion of the plane, or can I draw? Maybe, I don't know. It looks like that portion of the plane. So this is this, right? And when you look at this one, then I am saying that it is the same plane, but it is translated. How is it translated? Because when you have a plane, whenever you have a plane, right? So whenever you have a plane, you have a normal vector, right? So you have one vector which is perpendicular to it. And when I say translating, I mean translating parallel to that vector, right? Translating parallel to that vector. Otherwise, what does it mean to translate? So that C, it translates the plane parallel. But how do you say this properly? If v1, v2, v3 is a point on the plane, then right, yeah. So you should try to see that. I'm able to see it. There are 2 ways to see it. You should think about it. Why that other one, that C? So clear way to clear question is this. You look at this geometric object, G1. Look at this geometric object. Both of them are planes. First see that, and then show that these 2 planes are parallel. Okay. Trivial thing if you know the theory. Otherwise, you should just think and experiment. You can answer this. It's a 3-dimensional thing. Think about it. So in that's why it doesn't happen. But here, I first of all, I should know why it doesn't happen. So yeah, just let me think a little bit. So line will always be there, but then yeah, that is why, right? If you have a plane, you have another plane, and they cut. And if I and how does it happen? So two planes parallel. Yeah, it's more complicated, but it can happen. Yeah, so it's something like, but then yeah, let me not say it right now. Basically, when you translate them in different by different amounts, they can stop intersecting. Yeah, like like yeah, like for example, yeah, three lines. I can say three lines, they intersect, right? But when you translate one of them, then there may not be any common intersection point. Okay? Translate it parallelly only, like to some with respect to some meaning, but they can stop, yeah, having a common solution. So something like that. But let's not go into all that. There are other ways to see it. But okay, so let's stop this and finish this with, yeah. So we have done those things. Now let me just give you some homeworks to think about. I think that's the best way to get some work done. Yeah, now there are other questions, but as usual, we have not done them today. Try to do them yourself, but we will do it if you cannot do it. Okay, so some homework coming. So suppose A is a m by n matrix. So this equation 1. So show m less than n implies there are infinitely many solutions. Okay, m equal to n and m equal to n and unique solution A is invertible. These are the keys into getting better, connecting all the system of equations with theory of matrices. It's a back return favor, right? Because these like matrices are being used as a tool to solve equations, but now understanding equations, so you can talk about invertibility in terms of the equations corresponding to the system. This is the fun. And m greater than equal to n, not much can be said because it can effectively be n less than equal to n. So we'll leave that. So this is just a very elementary exercise, but yeah, let me give you the more interesting exercise. So let me write here B. And this is what I was saying. This kind of thing will be useful in all sorts of things because it's a very general thing. Cosets, differential equations, solution. Basically, how good is making a guess? How effective can it be? And it can be rather effective, very, very effective. So now we have put a B there. So you understand that B is a M given M thing. X equal to B, this is 2. So this is for 1 only, not for 2. Yeah, it's not for 2. Doesn't apply to 2. For 2, yeah, you can see the intuitive. If you cannot do this, at least do this for small cases. So, yeah. So what I'm saying is that okay, I'll stop writing m cross n. Understood. Ax not equal to b. So by this I mean it's a particular solution. Okay. So if Ax not equal to B implies that all solutions can be said. So how? Implies that Ay equal to B, which means if y is another solution, implies. So I am saying it also. So I'm unwrapping it for you so you can write it properly. I'm just writing it in a short way. Ay equal to B implies that y is equal to, or rather, if not this, y is equal to x naught plus x for sum Ax equal to 0. What am I trying to say? I'm saying that you take a solution, if you can guess a solution, if you can guess one solution, x naught, then every other solution y, okay? So if y is a solution, some other solution, then that solution is nothing but the solution which you got by guessing and adding to it some solution of the homogeneous version okay? And in this way you can get all solutions. That's is not surprising if you think about it. Yeah, so let me write one more maybe. So you know this thing. So now we will so you see this number 2 tells you that you don't have to worry too much about the B. So stop worrying about it in this question. Right. So you know this thing that Ax equal to 0 if and only if Ea x equal to 0, where E is invertible. So I'm writing invertible like this now from now on. You will see later why general linear group. It's invertible matrices. Why the word general will be clear later, and why linear also will be. This thing you know. So this tells you that start with a matrix, then you can look at its, you can finally go down to the row reduced echelon form. This may be a little difficult. So uh, you can find a solution there, and solution initially don't change, which is what we have been using. So you can simplify as much as you want, provided you only do the row operations, not the column operations. So what can I ask here? I cannot ask anything unless I define row reduced echelon form properly. Then I can ask that prove that it is unique. That is a nice exercise, which I find is not there in Hoffman and Kunz also. Which once I was solving took me several hours. It was easy. So let me not ask. But still, you should ask something. This is already written. Mm, ah, I'm just thinking some creative exercise because standard ones you can find in the books, in standard books. But all those things need more this. Yeah, right. Uh, no, I don't think. Okay, leave it. Okay, so we will not talk about. Okay, so this is it for today. Okay, we have developed some more things, so maybe this will help you to solve the later question. I think I think it's already most of it is easy now. Maybe 2.9, 2.10 we can. Okay, so we will meet as usual Thursday. Okay, Thursday 8:30. Please work as much as you can. Very important. All right then. That's it.
Yes. Okay.
Bye.
Yes, sir. Thank you, sir.